In this section, we're going to take a look at the polar form of complex numbers, as well as de Moivre's theorem.
Go ahead and recall from college algebra that we define the imaginary unit as the square root of -1. Okay? Alternatively, you can write I squared is equal to -1. Either of these is an acceptable definition for the imaginary unit. Okay? When you first learn about the imaginary numbers and the complex numbers by extension, one way you can represent them is by thinking about them as points on a plane. Whenever you have real numbers, then you can think of those as points on a number line. Here, this would be 0, 1, 2, 3, and so forth on forever to the right, and -1, -2, and -3 as points on forever to the left. So if I wanted to find the number 1, well, there it is. It's a point on the number line. If I want to find the number -2, well, then there it is. There's a point on the number line. But when you're dealing with complex and imaginary numbers, you note that there's no place to put them on the number line, because the number line is completely filled with all of the real numbers. So in order to give us a visual representation of our complex and imaginary numbers, we don't use the number line, we use the complex plane. The complex plane is a set of number lines, one of which represents the real numbers. It's the same number line that you're used to. All right, it's the same as this one here, with 0 in the middle. But then this other number line represents the imaginary numbers. This would be I, this would be 2I, 3I, 4I, and so forth. And likewise, you'd have your imaginary numbers down here as negative. So -I, -2I, -3I, and so forth. So when you look at a complex number, what you want to do is you want to consider it as a point not on the line, but on this plane. So, for example, let's say I have this point here. This is now 3 plus 2I, just like that. Now, notice that there's still a place for all the real numbers. If I want to find the number 1, well, there it is. And if I want to find -2, there it is. And if I want to find imaginary numbers, there's a place for those too. If I want to find the imaginary number I, there it is. And -2I, there it is. But if we want to look at a complex number, then that's actually not going to rest on either of these number lines, but rather it will exist somewhere in one of the 4 quadrants here. So, for example, this point right here would be 2 to the left and 1 up. So 2 in the negative real numbers and 1 in the imaginary numbers. So we could write this as -2 plus I. And every imaginary number rests on this number line. Every real number rests on this number line. And all the stuff in between are the complex numbers, those numbers that are a combination of real and imaginary. But now notice, these points on this complex number plane, well, they are points on a plane, which means I can consider them as the endpoints of a particular vector. So whenever you have a complex number, you could think of it as a number. You can think of it as a point on the complex plane. However, for the purposes of this section, we're going to consider it as a vector that starts at the origin. Whenever you have the origin, 0, 0, you can go out to this point, and this designates a vector. This is called the polar form of a complex number, and it allows us to consider complex numbers as vectors on a plane. Okay, so how do we do that? Well, let's consider a complex number. Here, let's not worry about any specific number. Let's just take a generic one. So here is the complex number x plus iy. Okay? Just like 3 plus 2i, here I'm going to say x plus iy. All right, well now, notice that this vector, to get from here to here, we'd have to go x units to the right from the origin here. We have to go x units to the right, and we have to go y units up. Oh, well, sure, that's the way complex numbers usually work. This, the first coordinate, left and right. Your second one gives you a second coordinate, up and down. Well, yeah, but now I can think of this as being, well, if this distance right here is the real number, the one that doesn't have an imaginary unit, I can think of that as an angle theta, and I can think of this as being the magnitude of the vector from here to here. This magnitude, whenever we're talking about vectors, usually we write it with the double bars, kind of like absolute value signs. But whenever we're dealing with complex numbers, usually the way we're going to write this is using the symbol r. R stands for like radius. So you can kind of imagine this as being the distance from here to here. All right, well, if that's the case, then I note that to find this x value, I could use the sine, or the cosine of the angle theta. I note that the cosine of the angle theta is equal to the side opposite of theta over the hypotenuse, which is just r. And here, to find x, I can multiply r over to the other side to give me x is equal to r times the cosine of theta. Likewise, I could use theta to find this y. I could say the cosine of theta is equal to x over r. Well, then the sine of theta is equal to y over r, the side opposite over the hypotenuse. If I multiply the r over to the other side, I get y equals r sine of theta, like this. What that means is, if I have this complex number, I can write my complex number in a few different ways. I can write it as x plus iy as a complex number. I can write that, if I'm thinking about this as a vector, I can think of it as the vector x comma y. And here I'm writing it as a vector. Notice in the vector form I don't write I, because it's assumed that the second number, the second component, will be in the I direction. So here we explicitly write I, whereas here we just write the x and the y. And you could also write that vector, instead of writing it in terms of x and y, we can write it in terms of this distance, which is the magnitude of that vector, divided by theta, which is the direction angle of that vector. So here we can write this as r cosine of theta, comma r sine of theta. And this is our polar form. Just like that. Note that r is a common factor. In fact, it's a constant, because after all, r is just a number. It's a distance from here to here. So even though this is the correct polar form, more often than not, it's written like this: r times cosine of theta, comma sine of theta, with the r separate. And if you don't want to write it in the polar vector form, oh, actually, I should write that here, polar vector form, then we can go back to writing it like a complex number, where we're explicitly writing I on the second component. So here this is going to be r times the cosine of theta plus I sine, plus I r sine of theta. Or again, since r is a common factor, we can factor that out, and that gives us r times the cosine of theta plus I sine of theta. And this is the polar form of the complex number. So over here we have the standard form. And here we have either of these is acceptable as the polar form. So there's a few ways you can think about it here. Here's the standard way we usually write a complex number, 2 plus 3i, something like that. Here we can write it as a vector. Here we can write that vector using this substitution, because after all, if cosine of theta is equal to x over r, then x can be replaced with r cosine of theta. So that x gets replaced with that r cosine of theta. Y gets replaced by r sine of theta. So we can write this in the polar vector form. And again, either of these would be acceptable for that. But if you want to then take this form and write it back in terms of a complex number, Well, that's now a complex number. We're explicitly writing the imaginary number on the second component. But now, this complex number is not written in the standard form in x and y, but it's written using these this notation, r and theta. So that's the polar form of our complex number. So let's go ahead and summarize all of that. Given a complex number, x plus iy, and here I'm going to go ahead and label that as being the standard form. We can write the same number, the same complex number, as r times the cosine of theta plus I sine of theta. Notice that r would distribute into both of those, and this is called the polar form. Some books also call this the trigonometric form. You'll hear me say that sometimes, the trig form. Either one's fine. They both mean the same thing. Here, this r is the magnitude of the complex number, and that's given by the square root of, well, the same way we always find the magnitude of a vector. Take the sum of the squares of the two components. So here that would be x squared plus y squared, like this. Whenever you're dealing with the magnitude of a complex number, this is called the modulus of the complex number. And it's just the magnitude of the vector, r. And here, theta is going to equal to the inverse tangent of y over x. If this looks familiar, it's because it's the same conversion that inverse tangent. It's the same conversion that we saw when we were dealing with vectors in a previous chapter. Because, of course, that's what we are thinking about these polar, we're thinking about these polar forms as the results of thinking of a complex number as a vector. Here, r is the modulus. Theta is called the argument of the complex number. Okay, so let's take an example of this. Let's write the number 5, let's say minus 12i in polar form. Okay. Here, it's really convenient to give your complex number a name. That way we don't have to keep writing this over and over again. It's traditional to call real numbers x or y. It's traditional to call complex numbers z. Why? I have no idea, just because that's the way it was done when people started doing this stuff hundreds of years ago, and the convention just sort of stuck. So just like x1, x2, x3, x4, that's usually given for real numbers. If I write a variable x, we assume that means it's a real number. When we write a variable z, we kind of assume it means it's a complex number. All right, so we're going to write z in polar form. The polar form of a complex number requires you to know its modulus and to know its argument. All right, so let's go ahead and do that. First of all, let's find the modulus of z. The modulus of z, we can write that in shorthand by writing z in absolute value bars. You can think of the modulus of z as being the absolute value of z. You say, oh, how does that work? How is that an absolute value? Well, look back at the picture. How isn't it an absolute value? Remember, by definition, absolute value is your distance of your number away from 0. Here, the absolute value of 1 is 1, because that's how many steps away it is from 0. The absolute value of negative 2 is 2, because it's 2 steps away from 0. And now if you wanted to say, well, what's the absolute value of that complex number? Well, it's how many steps away it is from 0. It would be the length of this vector. Oh, but that length of that vector is what we're calling r. So here, it fits exactly the definition of the absolute value. So the modulus of z, you can think of that as being the absolute value, because it is. All right, so the way we find the absolute value of a complex number, well, here it is. We're going to take the square root of the sum of the squares of the components. Notice we don't worry about the I. Here we're treating this as a vector, and when we treat a complex number as a vector, we say x is the first component, y is the second component. The I is understood to be there, but we don't actually write it out. So here my components are just the x and the y, just these numbers, not the I. So here, my x is 5, and my y is minus 12, not the I. So here this will give me the square root of 25 plus, well, let's see, negative 12 squared is positive 144. So this will give us the square root of 169. Oh, that actually works out to be a whole number. That's 13. That was a coincidence. I just picked this number randomly off the homework, and this one just worked out to be a nice number. Oftentimes you end up with like the square root of 5 or something. It doesn't have to be nice. So here, that's your modulus. That's your absolute value of z. Okay, well that's going to go right there. Okay. So now let's go and find the argument of z. And you can think of that as being a direction angle. And that's simply given by the inverse tangent of y over x. So here that's going to be theta is equal to the inverse tangent of y over x. Here y is the second component, not including the I, just the number, negative 12. And 5, that's going to be our y, that's our second component. All right, that looks just like that. And now that should be inverse tangent, not tangent. There we go, inverse tangent. And so now we can go ahead and pop that off. If we take negative 12 over 5 and take the inverse tangent, that's going to be negative, approximately, negative 67.38 degrees. Just like that. So here we can go ahead and write our complex number in polar form by using these two pieces of information. Now you have to be careful here. This angle might be a little misleading. And say why? Well, remember the inverse tangent of a number, that can't be just anything. The inverse tangent of a number must be between negative pi over 2 and pi over 2. Or if we're talking in degrees, that's got to be between negative 90 degrees and positive 90 degrees. Okay, sure. That's what that is. That's between negative 90 and positive 90. Well, yeah, but not every angle is supposed to be between negative 90 and positive 90. So here, let's go ahead and give a quick sketch of our complex number to make sure that it's in the correct region. If it's supposed to be here or here, well then we're fine. That's between negative 90 and 90. But if it's supposed to be between here and here, we have a problem, which means we're going to need to take this and modify it slightly. All right, so let's see here. Negative 67 degrees, that would be down here somewhere. That's 0. Negative 90 would be over here, so negative 67 would be a little bit less. Okay, that's fine. So that's about negative 67.38 degrees. All right, now the number 5 minus 12i, that's supposed to be 5 units to the right and then 12 units down. Oh yeah, that's in the right place. Okay, so this does put us in the right region, so that is the correct angle. You say, well, what if that wasn't the correct angle? What if it had put us somewhere else? We'll see that in the next example. We'll see how to correct this when it's not correct. But for now, yeah, this works. This number is supposed to be in quadrant 4, and this angle puts me in quadrant 4, so that's exactly what I need. So here we can write z, which is that number up there, can be written as 5 minus 12i. It can also be written as 13, that's your modulus, times cosine of negative 67.38 degrees, plus I sine of negative 67.38 degrees. Okay? Just like that. Here there is a shorthand notation for this. Cosine of an angle plus I sine of an angle. Notice that this angle is always going to be exactly the same. It's always going to be theta there and theta there. These will never be different. So there's a shorter notation for this. You can write 13, and instead of writing cosine of this plus I sine of this, you can write CIS. That stands for cosine, and then later I sine. Cosine I sine of an angle, negative 67.38 degrees. Either of these is an acceptable answer. I will warn you, if you do choose to use this one over this, keep in mind that this is not just one expression. It is made up of two expressions. This will come in useful later. If you just think of this as one expression, it's going to be harder to do some things later on down the line. So if you want to write this to save time, that's fine. But do remember it is made up of two separate pieces. So let's look now at another example. Let's consider the same kind of question. We're going to go ahead and write, let's see. Let's do negative 2. Here, let me write that as z. So let's write z, which is equal to negative 2 plus, negative 2 plus 3i in polar form. We'll note that whenever we're writing something in polar form, we're going to need to find two things. We need to find the modulus. We need to find the modulus of z. And we're going to need to find the argument of z. Okay? So go ahead and pause the video and find those two. Find out what is the modulus of z. Find out what's the argument of z. And once you have that number and that angle, go ahead and unpause the video and I'll show you what to do with them. All right, so let's take a look at the modulus. The modulus is going to be found by taking the square root of the sum of the squares of these numbers here and here. So that's minus 2 and positive 3. Don't include the I, we're just including the coefficient here, this number. All right, well, that's going to be the square root of positive 4 plus 9, and that's going to be the square root of 13. And that one doesn't give you a nice, pretty number. I can't take the square root of 13 in any meaningful way. I guess you could type that into a calculator, but then you're going to be carrying around this big old number for the rest of the problem. And you're better off just writing square root of 13 rather than writing that big old number. So here, that's your modulus. Now, theta, the argument of our complex number, is going to be the inverse tangent of, take your y, which is 3, over your x, which is negative 2. And here I'm going to take the inverse tangent of negative 1.5. Right? So here, if I take negative 1.5 and take the inverse tangent, that is going to give me approximately negative 56.30. Here, let me just write this 31. I'll round it off to 2 decimal places. Here, we don't generally even need to round it off. Again, this is the precise form. This is what we'd want to use. But here, let me go and round it off just for the sake of the explanation. Okay? So here are your modulus and your argument. And here's an estimate of your argument. Now, notice that this complex number rests in the second quadrant, which is, here, I went left by 2 and up by 3. So I'm over here somewhere, right? Left by 2 and up by 3. I'm over here somewhere. But notice that my angle is negative 56 degrees. That's the wrong direction. Because an angle always starts off with the positive half of the x-axis. Negative would go clockwise. This would be negative 90. So negative 56 would be somewhat less than that. So this is the angle negative 56.31. But notice that's in the wrong direction. That's in the fourth quadrant. What we need is in the second quadrant. Oh, but also notice from the illustration that they're exactly opposite of each other. So if you take this angle and add, well, that's half a circle, right? A full circle is 360. Here I want to go half circle, so that's 180. That'll give me the actual angle that I need. So here, this angle that I want right here is going to be what I get whenever I start with negative 56.30. So here, let me call that one theta. But that's not the one I really want. What I want is this one over here. So let me call this one, I don't know, gamma. Right here, this whole thing is 180. But I know this one, so I can figure out this one. All right? So let's take our negative 56.31. That starts us off down here at this vector. Now if I add 180 degrees, that'll put me in this direction over here. And if I add that, that's going to give me 123.69. 123.69, which is the angle that I actually want. Right? So that's going to be our angle gamma. All right, so now I have my modulus, and I thought I had my argument, but it turns out that was in the wrong direction. So it turns out that my real argument should be this one. That's going to be the nice thing about this. If you have the right argument, well, then that's right. If it's not the right argument, all you need to do is add 180, and that'll get you the right argument. Here, to make sure that you have the right argument, go ahead and check by drawing this out. If it's in the right direction, awesome, just leave it. If it's in the wrong direction, go ahead and add 180, and that'll get you your result. So here, this was not the right angle that I wanted. I actually want this angle down here. So this is my actual argument. So now we can write z as, we're going to take our r, which is the square root of 13, cis of this argument, not this one right here, 123.69 degrees. And that is our result. Of course, we can always go backwards. We can start with something that's in polar form and go back to rectangular form. And that one's actually a lot simpler because the conversion is a lot shorter. For example, let's say we're going to, instead of writing it in polar form, let's say we're going to write, I'm going to take 5 cis of, I don't know, let's say 30 degrees. Write that in standard form. Incidentally, depending on what book you're using, standard form is also sometimes called a rectangular form, because it's on the rectangular coordinate system, the XY coordinate system. All right, conversion back into standard form doesn't require you to remember any of these formulas. It just requires you to know how to do arithmetic. Here, let me write that as z. Z is equal to that. Here, z is equal to, let me write this out the long way. CIS of 30 degrees really means cosine of 30 degrees plus I times the sine of 30 degrees. Oh yeah, but I know those numbers. The cosine of 30 degrees is the square root of 3 divided by 2 plus the sine of 30 degrees is 1/2. Oh, but now I just need to multiply. So multiply 5 there and multiply 5 there. After all, you're just distributing a number into a binomial. You distribute. So here that's going to be 5 root 3 over 2 plus I times 5 over 2. So I times 5/2. And there we go. There is our complex number back in standard form or rectangular form, depending on which label you like. So go ahead and give that a try. Go ahead and write z equals to 2 cis of, let's say, 20 degrees in standard form. Note that over here, 30 degrees was something I could do in my head, right? Sine of 30 degrees, cosine of 30 degrees. Those are something that we've known since chapter 1. But this one is going to be a little bit harder, cosine of 20 degrees and sine of 20 degrees. So in this case, an approximation is fine. Right? So go ahead and give that a try and see what you get. Once you have a result, go ahead and unpause the video and we'll go through it together. And again, this can be done by just writing it out the long way. So that's going to be 2 times CIS of 20 degrees really means cosine of 20 degrees plus I times the sine of 20 degrees. All right, well, we can find both of those numbers. If we wanted to, we could figure this out using some of our identities. We actually can figure out exactly what the cosine of 20 degrees is. Right? But here, an approximation will be fine for now. We're going to take the cosine of 20 degrees, and that's going to be 0.9397. I believe this book rounds all of these numbers off to 4 decimal places, so I'm just going to go ahead and follow suit. They round all their degrees to 2 decimal places, and they round all of these to 4 decimal places. That's just the way the books decided to do it. There's no reason why 2 is a special number of digits. There's no reason why 4 is a special number of digits. That's just what they've done for all of their examples to be consistent. So I'm going to go ahead and follow suit. Same thing right here, sine of 20 degrees. Well, that's about 0.3420. And now you're just going to take that number 2 and distribute it throughout. So if you take 2 times 0.9397, you end up with 1.8794 plus I times, and if you multiply these out together, you're going to get 0.6840, just like that. Here, I'm going to write the I on the end, and that's just aesthetic, meaning that's just for the way it's going to look. Usually whenever you have an actual digits or set of digits here, we write the I on the end. If you write it on the front, it does mean exactly the same thing, but you'll notice that oftentimes whenever we have a digit or set of digits, we write the I on the end. And again, that's just conventional. That's just the way it's usually done. If you do write the I in the front, that's acceptable as well. And there we go. That's our value z in the standard form. When you add or subtract complex numbers, it's very, very simple. All you do is you combine the real with the real and the imaginary with the imaginary. So for example, if you have 2 plus 5i, and to that you want to add negative 8 plus 6i, well then all you're going to do is you're going to add the real number with the real number. 2 plus negative 8 will give me negative 6, and add the imaginary number with the imaginary number. 5i plus 6i will give me 11i. Subtraction is just as simple. You can take something like 3 plus 4i minus 7 minus 3i and subtract. And again, you just real with real, imaginary with imaginary. 3 minus 7 gives me negative 4. 4 minus a negative 3, well, that's the same as 4 plus 3. 4i plus 3i will give me 7i. Just like that. Okay. Multiplication is slightly more complicated, but not much so. Because if I have 4 plus 3i times 2 minus 5i, notice that I'm multiplying a binomial expression times another binomial expression. So I need to distribute. 2 times 3 is equal to 6. 3 times minus 5i is minus 15i. 4i times 2 is 8i. And 4i times minus 5i is minus 20i squared. All right, negative 4 times 5 is negative 20. I times I is I squared. Now remember, by definition, anytime you have I squared, it's supposed to equal to negative 1. So here, when we say negative 20 times I squared, what we really mean is negative 20 times negative 1. Okay, so that's actually a real number right here. That's positive 20, and then there's another 6 over there. Okay, so positive 26. And then these are both imaginary. Negative 15i plus 8i is going to be negative 7i. And there we go. That's a little bit more complicated, but you still get a nice answer, even with a few extra steps. Well, now the problem with multiplication that you don't really have with addition or subtraction is it gets significantly harder when you add a third number. What I mean by that is look at addition. Let's say instead of adding two imaginary numbers, two complex numbers, let's say I added three of them. 5 plus 7i plus 2 plus 4i plus, let's say, 3 plus 9i. That doesn't really get much harder because you're still adding the real with the real. 5 plus 2 is 7, plus 3 more is 10. And here, 7i plus 4i is 11i, plus another 9i will give me 20i. And yeah, it does take me slightly more time because I will have to add two numbers instead. I have to add three numbers instead of two, but it doesn't really take that much more effort. Subtraction will work the same way. It's not going to require a lot more effort to have a third number, or a fourth, or even a fifth. If I had 5 complex numbers that I was adding together, sure, I'd have more numbers to add, but it doesn't really take a tremendous amount more work. Multiplication, on the other hand, is significantly bigger. Because if I take 3 plus 4i times 2 minus 5i times 7 plus 3i, notice that it takes all of this work just to do these first two. And then once I have those two, I still have to distribute this one. So here, this is all of this work is required to tell me that these two multiply together to give me 26 minus 7i. But now I have to multiply times this one, and this one will also require that much work. 26 times 7, that'll give me 182. So that's going to give me 182. 26 times 3i, that'll give me 78i. And then negative 7i times 7i will give me negative 49i. And then negative 7i times positive 3i will give me negative 21i squared. But again, we know that I squared is the same as negative 1. So here, that's going to just give us negative 21 times negative 1. And now we can combine. Negative 21 times negative 1 is positive 21. And if I add that to 182, I get 203. And then combining these, if I take 78 minus 49, I get 29i. So notice, to just multiply in one more complex number required 1, 2, 3, 4, 5, 6, 7 more steps. So multiplying complex numbers can become very, very big the more of these I have. That's what this section is going to be about. It's going to show us that, yes, we can multiply complex numbers by distributing. But whereas addition and subtraction don't really get much more complicated the more of these you have, multiplication will get significantly more complicated if expressed in this form. What we want to do is we want to express it in a different form, which will utilize the polar form that we saw in a previous section. So let's go ahead and look at that. So this is a theorem which begins with a couple of complex numbers. We're going to let z, and here I'm going to have two complex numbers, so I'm going to call this one z1. Let z1 be given by r1 times cosine of theta 1 plus I sine of theta 1. Here the ones aren't doing anything to the r or to the theta. You're not doing anything with that number 1 other than using it as a label. This is the r that goes with this z. This is the theta that goes with this z. And here we're going to take another complex number. We're going to call it z2. And that's going to be r2 times cosine of theta 2 plus I sine of theta 2. Okay? So you're starting off with two complex numbers in polar form. That's the important part right here. Assuming that that's what z1 and z2 are, you can write z1 times z2 as r1 times r2 times the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. What this is saying is if I give you two complex numbers in polar form, you can multiply those polar forms by multiplying their modulus and by adding their arguments. There's something about multiplying complex numbers that causes the angles, the direction angles, to be added instead of multiplied. So let's see why that should be true. Oh, incidentally, this is called the product theorem. This is the product theorem. So let's see why this should be true. All right, let's take a proof of this. All right, well, let's take z1 times z2. Okay, well, we can just, if that's z1 and that's z2, well, let's just multiply those two things together. So that's going to be r1 times cosine of theta 1 plus I sine of theta 1. And that's going to get multiplied by r2 times the cosine of theta 2 plus I sine of theta 2. Okay, we haven't done anything other than just say, okay, if this is equal to that and this is equal to that, then multiplying those two is the same as multiplying those two. Okay, so multiplying those two is the same as multiplying those two. Now notice this is r1 times this times r2 times this. So I could just rearrange some terms. So here, let me put the r's together. All right, this is r1 times r2 times cosine of theta 1 plus I sine of theta 1 times cosine of theta 2 plus I sine of theta 2. Just like that. R1 times R2. Those are just two numbers that are getting multiplied. So I'm just going to leave those alone for now. But over here, these are not just two regular numbers, they're complex numbers. And we already saw that when we multiply complex numbers, we have to distribute. Okay, so let's do that. That's going to give us R1, R2 times, all right, well, let's distribute. Cosine of theta 1 times cosine of theta 2. Cosine of theta 1 times I sine of theta 2. Okay, well, there's an I on that one, so I'm going to write that as plus I cosine of theta 1 sine of theta 2. Over here, that's also going to have an I on that one, so that's going to be I sine of theta 1 cosine of theta 2. And finally these, that's going to be I times I is going to give me I squared sine of theta 1 sine of theta 2. Just like that. Okay. Now I notice that I have a few things that I can rearrange. Notice both of these are real. And you say, no, that one's not real. That's got an I squared on it. Well, yeah, but remember, by definition, I squared is equal to negative 1. So right here, instead of saying plus I squared times this, I can take this I squared and just replace it with a minus 1. So really that's just, instead of saying I squared times this, that's just negative 1 times this, which really just turns this into a minus. There's no more imaginary on this, and there's nothing else imaginary on this, so these are both real. So let me lump those together, and I notice both of these have an imaginary number, so let me put those together. So I'm going to rewrite this as R1 times R2 times, let me put the real ones together, cosine of theta 1, cosine of theta 2, minus, that's now a negative, sine of theta 1, sine of theta 2, okay, plus I times the cosine of theta 1 times the sine of theta 2, plus I times the sine of theta 1 times the cosine of theta 2. Notice right here that these two both have an imaginary number on them, which means that the imaginary number I is a common factor. So I can factor that out. So I can write this as R1, R2 times the cosine of theta 1 cosine of theta 2 minus sine of theta 1 sine of theta 2. And I'm going to go ahead and put that in parentheses. All of these are real, so let me go ahead and keep those together. And then plus, notice I have an I. That's a common factor, so let me factor that out. And once I factor out I, let me keep all that stuff in parentheses. Cosine of theta 1 sine of theta 2 plus sine of theta 1 cosine of theta 2. Just like that. But now, take a moment. Do those look familiar? Think back to our chapter 5 and think back to our identities. If you take the cosine of an angle times the cosine of an angle minus the sine of an angle times the sine of that other angle, this is just the sum formula for the cosine function. Here, you can write this as R1, R2 times all of this stuff is just going to be cosine of theta 1 plus theta 2. That's because all of this becomes just that small expression using the sum formula for cosine. Likewise here, there's a plus I times something. Well, that something, this you might recognize as being the sum formula for the sine function. So here that's going to be the sine of theta 1 plus theta 2. Just like that. And again, that is just the transformation from here to here is just the sum formula for sine. Oh, but that's what we wanted, because now notice z1 times z2 is equal to r1 times r2 times the cosine of the sum of theta 1 and theta 2 plus I times the sine of the sum of theta 1 and theta 2. So that's exactly what we wanted, and that concludes our proof. So let's see an example of this. Let's say we're going to multiply two numbers together. So example, let's let z1 equal to 5 times the cosine of the angle, let's say 20 degrees, plus I sine of 20 degrees. Incidentally, you can also write this in the CIS notation, but here I'm going to write it out the long way so that it looks more like our theorem. But if you're comfortable using the CIS notation, as long as you keep it straight, it does mean the same thing. Here I'm going to go ahead and say z2 is equal to 2 times the cosine of, let's say 40 degrees plus I sine of 40 degrees. So now if I want to multiply those two together, z1 times z2, that's just going to be multiply these two together. That's 2 times 5. And then here you're going to take cosine of an angle plus I sine of an angle. And that angle is simply going to be the sum of these two angles, 20 degrees plus 40 degrees. So here that's going to give us 10 times the cosine of 60 degrees plus I sine of 60 degrees. And that's it. You multiply the two modulus and you add the two arguments. This doesn't get any harder, or doesn't get significantly harder if you have 3 of them. So for example, let's say you take z1 is equal to 2 times the cosine of 10 degrees plus I sine of 10 degrees. Let's say z2 is equal to 3 times the cosine of 5 degrees plus I sine of 5 degrees. Let's say z3 is equal to 4 times the cosine of, let's say 15 degrees plus I sine of 15 degrees. And let's say z4 is equal to, let's say, negative 2. Oh, no, that's a modulus. It's supposed to be an absolute value, so that can't be negative. So let's keep that as a positive. Right? That can't be negative. It's a modulus. It's the absolute value of a complex number. It cannot be negative. So let's say we have 2 times the cosine of 20 degrees plus I sine of 20 degrees. We saw previously that if you multiply out complex numbers just by distributing, that becomes very, very complicated. But if we're using the product theorem, z1 times z2 times z3 times z4 should be fairly straightforward to do. So go ahead and pause the video, give it a try, and once you have a result, go ahead and unpause and we'll go through it together. Alright, so let's take a look. Here we're simply multiplying these together. So that'll be 2 times, well here let's write that out. 2 times 3 times 4 times 2. Alright, you're going to multiply together all of the modulus. And you're going to go ahead and add together all of the arguments. So this is the cosine of 10 degrees plus 5 degrees plus 15 degrees plus 20 degrees. And then same thing for this one, plus I sine of 10 degrees plus 5 degrees plus 15 degrees plus 20 degrees. So total, that's going to give us, well, let's see, 2 times 3 is 6, times 4 is 24, times 2 is 48. So it's going to be 48 times the cosine of 15 plus 15 is 30, plus 20 more is 50. So as you note, that is significantly cutting down the amount of effort that it takes to multiply things together, because now instead of having to do the full-on distribution, we simply multiply these together and add these together to get our result. All right. Note that this can be used for things that are not in polar form, because of course you can always write them in polar form. So let's consider the example z1 is given by, oh, let's just keep things nice. Let's say this is, let's say z1 is equal to negative root 3 plus I. Note that's the same as saying 1I. And here let's make z2 equal to 4 root 2 plus another 4 root 2I. Like that. Go ahead and convert both of these into polar form. Write them as a modulus times the cosine of an argument plus I sine of an argument. And once you have both those written in polar form, go ahead and use the product theorem to multiply those two numbers together. All right, so go ahead and pause the video, give it a try, and whenever you're done, go ahead and unpause and we'll go through it together. All right, so let's take a look here. Let's go ahead and find R1. Remember, R1 is simply given by the square root of the sum of the squares of the components, the real and the imaginary, of our first z. So here that's going to be negative root 3. We're going to square that. Here that's 1i, so we're going to take that 1 and square that. And that'll give us the square root of negative root 3 squared is just the number 3. 1 squared is just the number 1. And that'll give us root 4, which is just the number 2. Okay, so there's our modulus of R1. There's our modulus of Z1, rather, which we're going to call R1. And now let's find the modulus of Z2, which we call R2. And that's going to be the square root of the sum of the squares of 4 root 2 and 4 root 2. Okay, so that's going to be the square root of, here if I take the square of 4, that'll give me 16. And then if I take the square of root 2, that just gives me 2. So here I'm going to have 16 times 2, which is 32, plus another 32, which will give me the root of 64. So here that's just the number 8. So I find the modulus of both of those. And now let's go ahead and find the argument. Here the argument theta 1 is given by the inverse tangent of, take your b, which in this case is 1, over your a, which is negative root 3. And then that'll give us, oh, that one actually works out to be a nice number. That's 30 degrees, I believe. Right? If I take 1, oh, that should be negative 30 degrees then. If I take 1 divided by negative root 3, and I take the inverse tangent, that'll give me negative 30 degrees. Okay, so that's negative 30. Now remember, with these can be a little misleading. So make sure that you're in the right quadrant. If you're in the right quadrant, great, that's your argument. If not, you need to add 180 to this to put you in the right quadrant. So let's just go ahead and quickly visualize where our point should be. Here, that's supposed to be negative root 3 plus 1i. So go back along the real numbers and up along the imaginary numbers. So here my z should be pointing in this direction. z1 is over here somewhere. Oh, but negative 30 degrees, starting from the positive half of the x-axis, I would go negative is clockwise 30 degrees. Oh, that's the wrong direction. Okay, so here, this isn't really the argument. I should have the one in the opposite direction. So that means here, that's the wrong one. I really should have negative 30 plus 180, and that's going to give me this angle. So here the angle I really want, my actual argument for Z1, is 150. Okay, so be very careful with that. Whatever your calculator gives you may not be correct. All right, it may be in the wrong quadrant. If it is correct, well then fine. You're in the right quadrant, so that's the one you want. But here, we don't want something in the fourth quadrant. We want it in the second quadrant. So we need to add 180 to put us in the right direction. All right, so here we go. Z1 is equal to 2 times the cosine of 150 plus I sine of 150. Okay, don't use negative 30. That would be incorrect. That would not be Z1. Over here, we can find theta 2 the same way. Theta 2 is given by the inverse tangent of y over x. So 4 root 2 over 4 root 2. Oh, that's the inverse tangent of 1. Oh, and that's 45 degrees. All right. If I take the inverse tangent of the number 1, that's 45 degrees. All right, so 45 degrees. Oh, okay. Well, again, let's double check. Let's make sure it's in the right quadrant. Here, that's positive and that's positive. So to get to Z2, I need to go to the right and up. That would put me in the first quadrant. The angle 45 degrees, starting from this positive half of the x-axis, since it's positive, I would go counterclockwise 45 degrees. Yeah, that's right. That does put me in quadrant 1 the way it's supposed to. This is in quadrant 1. This angle puts me in quadrant 1. And so this is the correct theta. Over here, it was not the correct theta. We had to adjust it. We had to correct it. So here, theta 2 is going to be given by 8 times the cosine of 45 degrees plus I sine of 45 degrees. Notice that when you have just two complex numbers, this is kind of a long process. You would never really multiply complex numbers using the product theorem if you just had two of them. It's really meant for when you have lots of them. You know, when you have lots of them, then you save yourself a lot of time by being able to do this. If you were just supposed to multiply these two, you would probably just do the distribution. It's not that long, and here, this seems a bit longer. All right? So yeah, the product theorem will get us this answer. That being said, you probably wouldn't use the product theorem for just two. You save it for when you need it, when you have lots of complex numbers. But here we can use it. Here, theta 1 times, Z1 times Z2 is going to equal to, well, we're going to multiply our two modulus, that's 2 times 8, times the cosine of, now I'm going to add my two arguments, 150 degrees plus 45 degrees, and same thing over here, plus I sine of 150 degrees plus 45 degrees, which will give us, well, let's see, 2 times 8 is 16. Cosine of, if I add these, that's 195 degrees, plus I sine of 195 degrees. Just like that. And that does give us our result. Okay. All right, now, Along with the product theorem, there's a related theorem, which is called the quotient theorem. This will allow us to not just multiply, but also to divide complex numbers. So let's take a look here. It's going to look very much the same theorem, and this is called the quotient theorem. And it starts off very much the same way. We're going to start off with two complex numbers. Let's let Z1 equal to R1 cosine of theta 1 plus I sine of theta 1. And we're going to take a second complex number, and we're going to take Z2 to equal to R2 times the cosine of theta 2 plus I sine of theta 2. Just like that. The quotient theorem says something very similar to the product theorems. The product theorem tells us that if I want to take those two complex numbers and multiply, I'm supposed to multiply these modulus, and I'm supposed to add these arguments. Well, here I'm not multiplying, I'm dividing. Well, multiplication is the opposite of division, so let me do the opposite of what I would normally do. To multiply these, I would multiply the two moduli. Okay, so let me divide the two moduli. And to multiply these, I would add the two arguments. So to divide, well, let me subtract the two arguments. So here that's going to be cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. Just like that. We're going to forego the proof of this one, mostly because it's almost exactly the same as the proof of the product theorem. Here what you would do is you would say, okay, well, if I put this one over this one, well, R1 over R2, okay, well, we just leave that alone. If we put this one over this one, what we can do is we can take this bottom one, multiply by its conjugate, that'll turn it into a real number. Multiplying the top by the conjugate, I'll distribute and I'll discover the difference formulas for sine and cosine. So here, the proof of this one is almost exactly the same except for one extra step. With this over this, I would multiply both top and bottom by the conjugate of this one. It would make this one a real number. In fact, if you do it, you'll find that the real number is the number 1. But if you multiply this one by the conjugate of this one, it expands out to give you the difference formulas. So here, we're just going to go ahead and say the proof is omitted, partially because it's very much the same as what we've already seen. So we're not really gaining much by seeing another proof that's so similar. So here it's omitted. Incidentally, if anyone who is going to go past trigonometry, going into calculus, differential equations, or beyond, anyone who fancies themselves an engineer, a mathematician, a physicist, you may want to actually try that just to give yourself experience on how to prove things, how to manipulate things in a theoretical form without any actual numbers in there. You might actually want to prove this. But for the purposes of this class, we're going to not worry about it. So let's just take a look at some examples of this. Let's take, for example, the quotient of the following two numbers. So here we're going to say Z1 is equal to 5 times the cosine of, let's say, 60 degrees plus I sine of 60 degrees. That's Z1. And let's take Z2 to be given by, let's say 2 times the cosine of, let's say 40 degrees plus I sine of 40 degrees. Okay? If we're going to take the quotient of those, if we're going to take Z1 over Z2, all we need to do is we need to take the quotient of their moduli. Take this modulus divided by this modulus, 5 over 2. And now we're going to take the cosine of, we're going to take the argument of the numerator minus the argument of the denominator, 60 degrees minus 40 degrees, plus I sine of that same thing, 60 degrees minus 40 degrees. And we can simplify that out to be 5 halves times the cosine of 20 degrees plus I sine of 20 degrees. Just like that. And that's our result. Notice that because this is a subtraction, the order does matter. So be mindful of that. If you have z2 divided by z1, that would give you a very different answer. You would take the modulus of z2 divided by the modulus of z1, and then this would be the cosine of, you take the argument of z2 minus the argument of z1. It's always the top minus the bottom. So here that's going to give you a negative number. So this would give you not 5/2 times the cosine and sine of 20 degrees, but you would rather have 2/5 times the cosine of negative 20 degrees plus I times the sine of negative 20 degrees. Right, so be mindful of that. The order does matter with division. With multiplication, it didn't. But there's our result. Consider the fact that we can square things by multiplying them times themselves. Yeah, so, well, let's say I have z is equal to r cosine of theta plus I sine of theta. Let's say I have a complex number in its polar form. Oops, that should be an r over there. All right, well, now let's say I want to take that, and instead of multiplying it by something or divided by something, let's say I wanted to square it. Well, you know, that is multiplying. After all, multiplying z times itself, that's what it means to square z. Oh, so that means we would take r cosine of theta plus I sine of theta, and we would multiply it times another r cosine of theta plus I sine of theta. But as we've seen in a previous section, if you're multiplying two complex numbers in polar form, that's accomplished by multiplying their moduli together and by adding their arguments together. So that would be r times cosine of theta plus I times the sine of theta plus theta, which of course can just be written as r squared, r times r is r squared, times cosine of 2 theta plus I sine of 2 theta. So what that means is if you have a complex number in its polar form, to square it, you just need to square the modulus and double the arguments. But what if I wanted to cube it? What if I wanted to say z to the third power? Well, notice z to the third power is z squared times z. Or in other words, it's the thing that I just wrote down, which is z squared, times r cosine of theta plus I sine of theta. All right, here's z squared times z, which is given the product theorem, r squared times r, times the cosine of the sum of these, which is going to be 2 theta plus another theta, plus I sine of the sum of these, 2 theta plus theta. And so that's going to give us r to the third power. R squared times r is r to the third power. Let's write this on its own line. R to the third power, cosine of, 2 pi plus another pi is 3 pi, plus I sine of 3 pi. Okay. Oh, well, notice, if I have z, that's r cosine of theta, I sine of theta. If I have z squared, well, that's the same r, but now it's being squared. And that's the same theta, but now it's being doubled. If I have z to the third, well, that's the same r, but now it's being raised to the third. And that's the same theta, but now it's being multiplied by that number 3. Okay. This brings us to our theorem of the section. Let z be given by r cosine of theta plus I sine of theta. In other words, let z be a complex number that's written in its polar form. Then z to the n is equal to r to the n times cosine of n times theta plus I sine of n times theta. This is called de Moivre's theorem. In fact, I probably should have written that first, but let's go ahead and write it over here to the side. This is called de Moivre's theorem. In mathematics, there's a convention that if you are the first person to discover a mathematical truth, oftentimes we name the theorem after you. So this was named after the mathematician Abraham de Moivre, who discovered this in the early 1700s. All right? So here, de Moivre's theorem allows us to take a complex number in its polar form and raise it to a power, and that's done simply by raising the modulus to that power and then multiplying the argument by that power. In other words, times n. Here, the proof of this is not something you can do just yet. It requires something called induction. So here you see the sketch of the proof. Here you see, okay, I can kind of see why it should be true, but here this is only true for power 2, power 3. The theorem says it's true for every power. In order to do that, you need something called induction, which isn't something you do yet. For those of you who go past trigonometry and go into pre-calculus, you'll learn about induction. But for now, that is a theorem that we can't complete. So here I'm going to say proof left for later semesters. Here you can see why it should be true, but here this only shows it for power 2, power 3. Here, to show it for every possible power, well, there's an infinite number of powers. Right? Power 3, 4, 5, 6, 7, 8, 9, 10, and forever. So that requires something that you're not quite ready for. Those of you who go on to pre-cal, you'll see it. But for now, let's go ahead and use the theorem here. First of all, let's talk about a very simple example, and then we'll extend it to see how this is going to give us the ability to take square roots and cube roots and so forth. So let's consider something like z is equal to, let's say 2 times the cosine of 5 degrees plus I sine of 5 degrees. Okay. Now let me take z and raise it to the, let's say 8th power. If this was written in its standard form, I would have to take a complex number and multiply it times itself 8 times. That would require a lot of distribution. You have to distribute 4 times for every time you multiply a pair of these. So imagine how many that's going to be if you do it 8 times. On top of that, all of the addition and combining of like terms that's required to simplify. So doing this in the standard form would be very, very long. However, using de Moivre's theorem, we can see that this is nothing more than, okay, take that modulus and raise it to the 8th power. And then we're going to take this argument and multiply it times that power. Or in other words, going to take the 5 degrees and multiply it times 8. And same thing over here. That's going to be times 8. Oh, well, we can do this now. 2 to the 8th power, that's going to give us 256. And if you take cosine of 5 degrees times 8, well, that's going to give you the cosine of 40 degrees. Plus I, the sine of 40 degrees. That's the same number. And there we go. We just raised something to the 8th power, which normally would have taken a lot of work, simply by raising that to a power and multiplying that by a number. And that's our result. Okay. Here, go ahead and give this a try. Let's say z is equal to, let's say 3 times the cosine of 7 degrees plus I sine of 7 degrees. Go ahead and take z and raise that to the 5th power. All right. Go ahead and pause the video, and whenever you're done, unpause and we'll go through it together. And the computation is just as short as this one. We're going to take this modulus and raise it to the 5th power. And then we're going to take this argument and we're going to multiply it times that number 5, that power there, plus I sine of the exact same thing. 7 degrees times 5. 3 to the 5th power, 3 times itself 5 times. That's going to give us 243. 7 degrees times 5 will give us 35 degrees. And same thing over here, I sine of 35 degrees. And there's our result. In some examples, you may need to first convert into the polar form before you do this. That is well worth your time, considering how much faster it is to raise something to the fifth power using de Moivre's theorem. So for example, your question might read something like, let's say z is equal to, let's see, what happened to my color balance here? There we go. Let's say we'll take -1 plus I, let's do that one. Let's do -1 plus I, and we'll raise that whole thing to the sixth power. Well, here, let's write it in two stages. So let's say z is equal to that. And the question is find z to the sixth power. Or in other words, raise that to the sixth power. Obviously, one thing you could do is write -1 plus I times 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 -1 plus I. And then start distributing. That is not at all the way you want to do that. Here, the simpler way to do it is to take this and turn it into its polar form. All right, so let's see here. First of all, we need the magnitude, the modulus of z. That'll give us our value of r. And that's simply given by taking these components, the -1 and the 1. All right, that's 1i, so that second component is 1. You're going to square them. You're going to add them together and take a square root. So that's going to be the square root of 1 plus 1, which is just root 2. Here, let's go ahead and leave that like that. Decimals are difficult to carry around. It's easier to just write root 2. Theta is going to be given by the inverse tangent of your y, which is your second component, over your x, which is your first component. And that's just the inverse tangent of -1, which is -45 degrees. Just like that. But now, don't forget, we need to make sure that our result is in the right quadrant. So let's just double check. Maybe that's right, or maybe we need to add 180. All right, -45 degrees from the positive half of the x-axis. That would have us go clockwise. That's the negative direction, 45 degrees. So that's -45 degrees right there. So this angle puts us in the fourth quadrant. All right, -1 plus I. -1 means go to the left, and positive I would mean go up. Oh yeah, no, we're in the wrong quadrant. Oh, okay, so here theta, it shouldn't be -45 degrees. We need to flip this over in the opposite direction. So this should be -45 plus 180 degrees. Remember, if this is in the same quadrant, then this is the right answer. But if it's in the opposite quadrant, you need to add 180 to get the correct answer. And here, if you take -45 plus 80 degrees, plus 180 degrees, you're going to end up with 135 degrees. So that's your argument. So here, when we say we want z to the sixth power, that means we want the square root of 2 times the cosine of 135 degrees plus I sine of 135 degrees. And that we want to raise to the sixth power. But now, even though this takes a little bit of work to find the modulus and the argument, because of de Moivre's theorem, this last step is very short and simple. All we need to do now is take this modulus and raise it to the sixth power. Separately, we need to take the cosine of, and you're going to take your 135 degrees and multiply it by 6. Same thing over here. You're going to take I sine of, you're going to take your 135 degrees and multiply it by 6. Which, if we evaluate, let's see, root 2 to the sixth power. If you square root 2, you just get 2. So that will be the same as 2 to the third power. So that's just going to give you 8. Right? And if you multiply 6 times 135, that's going to be carrier 3, 810. Cosine of 810 degrees plus I sine of 810 degrees. And there you go. There's our result. Generally, this might look a little strange because we started off with a number in its rectangular form, in its standard form, and we ended up with it in its polar form. usually whenever we're asked a question in a particular form, you're kind of expected to have the answer in the same form, right? If your question starts off with a bunch of decimals, it would look weird to answer it as a fraction. If your question starts off in degrees, it's not usually that we answer it in radians. And same thing here. If you start off in rectangular form, it looks a little strange to write this in polar form. So even though this is the correct answer, let's go ahead and convert it back into the form that our original problem was in, which is, well, let's see. If I take the cosine of 810 degrees, that's something that's, let's just go ahead and pop this in here. The cosine of that is, it's actually 0. Is that right? Yeah, that's 0. The cosine of 810 degrees, that's going to be 0, plus I times, if I take the sine of 108, I keep saying that backwards, 810 degrees, that's just the number 1. So this is 0 plus 1i. Well, that was a nice one. I really did just pick these numbers completely at random. I picked a random imaginary number and a random power. I didn't expect for it to work out nicely. Oh, that was a nice surprise. So here that's going to be 8 times 0 is, well, that's 0. And 8 times 1i, that's 8i. And since you're adding 0, well, that's not going to change anything. So here that's just going to give you 8i. And that's your result. If you take negative 1 plus I and raise it to the 6th power, you're going to get 8i. Which, yeah, this takes a bit of work, especially here when we're converting this into polar form. But this is substantially simpler than actually taking negative 1 plus I times negative 1 plus I times negative 1 plus I, and so forth and so on. If you don't believe me, actually try that 6 times, and, well, it's not something I would recommend. Okay, so now let's assume that we have z is going to equal to r cosine of theta plus I sine of theta. Okay, so let's start off with a complex number in its polar form. You know, another way of writing z is by saying that it's going to be z to the power n nth root. After all, those should cancel out, right? If I take the z, raise it to the 3rd power, the 3rd root is a thing that cancels out the 3rd power to get me just my z. At least that's what would happen with a regular number, right? With a regular number, if I took the 3rd root of the number 5 to the 3rd, that would just give me the number 5. Right? If I took the 5th root of, let's say, 7 to the 5, well, that would just give me 7. That's the way it usually works. If I take the nth root of the nth power, I get z. Okay, just like I do over here. Okay, so then, well, what does that mean about this one? Well, what that means is that the nth root of the nth power should just give me back r times cosine of theta plus I sine of theta. Oh, but notice, this z is being raised to the nth power. So another way I could say this is, all right, look, I took r and raised it to the nth power. And you say, well, that's not the same r, right? That was some other thing that I took. Well, okay. So, yeah, it's still a modulus, but let me give it a slightly different name. Let me just call this S. Just to keep it from getting confused with that R right there. Okay? So that S, here, this, because that, whatever number that was being raised to the nth power, it should be raised to the nth power like this. By de Moivre's theorem, I should raise whatever argument, whatever modulus this had, raise it to that power there. And then whatever argument this had, I should multiply it times n. Right? So I could say that's something like, let me use something other than theta. Let me use alpha. And that's being multiplied times n. Plus I sine of alpha times n. Okay? So that's going to be z to the power n. Well, yeah, but I'm supposed to be taking the nth root of that. Okay, so what? Well, somewhere between here and here, these are supposed to cancel out. Oh, well, I know I can cancel this out by taking its nth root. So here this is s to the power n nth root. You say, well, how do you cancel this out? How do you cancel out multiplication so that I just get a regular argument without that extra number? Oh, well, to cancel multiplication, I have to use division. Okay, so this is going to be cosine of alpha times n over n. That way my two n's can cancel out. Plus I sine of alpha times n over n. And again, my n's could cancel out. So here, these two would cancel out, leaving me just a modulus. And here, these n's would cancel out, giving me an argument. But notice that that nth root, all it did was this nth root right here, all it did was contribute an nth root to my modulus, and it divided my argument by n. Right? Those were already there. Those were already there before I took the nth root. By taking the nth root, what it caused was it caused me to take the nth root of this modulus. Right? That wasn't there before. And it caused me to take this argument and divide it by n. Okay, so then that means that if I take the nth root of something, well then that's going to amount to taking the nth root of its modulus and dividing its argument by n. So that brings us to what's called the nth root theorem. So here's theorem. Go ahead and let z be given by r cosine of theta plus I sine of theta. Okay. This is just the counterpart to de Moivre's theorem, which states that, well, if instead of taking the nth root, let's say I take the nth power, oh, sorry, I said that backwards. Instead of taking the nth power, let's say I take the nth root of z, that's going to be accomplished by taking the nth root of r, and then taking this argument and dividing it by n. That should be divided by n also. And that's our result. Here, let's write that one out a little bit nicer. That's theta over n. Okay. All right, now, what this does is it allows me to take the nth root of a complex number, which is the first time we've ever been able to do that. So here, that's the nth root theorem. Just like de Moivre's theorem, we don't actually have a proof of this one that we're going to worry about. Here, this is not really a proof. This is just a sketch of, oh, okay, it looks like that should make sense, but this isn't really formally a complete proof, mostly because we don't have the ability to form a complete proof of de Moivre's theorem yet. So here we're going to say the proof of this would also be something left to a subsequent semester. Left to when math gets harder. You say it gets harder? Well, a little bit, yeah. Okay, so we're gonna forego the proof of that. That's something best left for later semesters, and let's just continue to see some examples. So let's take the example. Let's start off very simply with just the number I, and let's take a root of I. Let's say I'm going to take the cube root of I. Okay, just like that. All right, cool. First of all, turn this into its polar form, because that's how this theorem is going to work. All right, so here we're going to say find the cube root. All right, find the cube root of I. Okay, so first thing we want to do is we want to change this into its polar form. I is equal to, well, let's see here. First, let's find the modulus of I. Oh, well, that's just the number 1, right? Because here, the modulus of I is just like saying 0 plus 1i. Which, if I'm going to take the modulus of this, that's going to be the square root of 0 squared plus 1 squared. So that's going to be the square root of 1, which is just 1. All right, so the modulus of this one is just the number 1. The argument of I is going to be the inverse tangent of, well, again, your y is equal to 1. and your x is 0. Oh, well, that doesn't quite work out, does it? If you try to type that into a calculator, it's gonna spit it back out at you. If I take 1 divided by 0, that's undefined, and that from my calculator that means error. So here you say, well, then I can't do that. Well, sure you can, because remember, the inverse tangent is undefined, or rather the inverse tangent, the tangent is undefined whenever you're at one of the asymptotes, either positive pi over 2 or negative pi over 2. In fact, here, this might be better done if you look at the graph on the complex plane. I is simply straight down, right? Here's 1, here's minus 1. Here's I, and here's minus I. Minus I is this point right here. And if you notice, that is simply, well, it's 1 unit away from the origin, but in terms of an angle, I'm sorry, that should be positive I. I marked negative I, not that one. I want this one up here. Not that one. I want this one up here. Okay, so that's going to be 1 unit away from the origin, and my angle between the positive x-axis and the imaginary axis, that's going to be 90 degrees, or pi over 2, whichever one you like. So here, that's 90 degrees, or pi over 2, but I'll stick with degrees since that's what we've been using for most of this chapter. So here, the angle theta, if you try to type that into a calculator, it's going to spit it back out at you and say, no, I can't do that. But we can do that. Right? We know that the inverse tangent of something that's undefined. Oh, well, if I take the tangent of what number is it undefined? Oh, well, if I think back to the graph of tangent, that was 90 degrees, or pi over 2 radians. Or if you just look at a picture on the complex plane, you still get that theta must equal to 90 degrees. So be mindful of that. If ever it gives you something like this, you might be better off just looking at the picture and seeing, okay, what's the angle that makes that happen? All right, so here we know that I is equal to, well, here's its modulus, it's the number 1, times cosine of 90 degrees plus I sine of 90 degrees. Okay, just like that. But that's not really true. You say, well, no, sure it is. I can type that all in. Look, if I take cosine of 90 degrees, right, if I take the cosine of 90 degrees, that's 0. 0 times 1 is 0. If I take the sine of 90 degrees, that's 1. So that's going to be 0 plus 1i. Yeah, that's right. That's correct. Well, yeah, that's not wrong, but it's not really true. It's not the full story. Because remember, sine and cosine are periodic functions, which means that, okay, yeah, it's true 90 degrees would work, but so would going all the way around and then going to 90 degrees. I could do 360 plus 90, which is 450. And I could go all the way around twice. 720 plus 90, that's 810 degrees. There's lots of angles that this could work with. Yeah, so? Well, let's see what happens when I include all of them. So here I'm going to write this as I is equal to 1 times the cosine of 90 degrees plus 360 n degrees. Because remember, every time you add a copy of 360, that's going to bring you back full circle. So if I do it twice, 3 times, 4 times, 5 times, it'll bring me back full circle every time. Oh, let me go ahead and put that around here. And then plus I sine of, and again, I don't want to just write 90 degrees. I'll write 90 degrees plus 360 n degrees. Just like that. All right. So now what? Well, now by my nth root theorem, if I want to take the nth root of z, I'm going to take the nth root of r and divide these arguments by n. Well, that's what I'm trying to do. I'm trying to take the nth root of of z. Well, that's going to be the third root of I. So right here, I'm going to take the third root of I, and that's going to equal to the third root of r times the cosine of 90 degrees plus 360 n degrees, and we're going to be dividing that by 3. Whatever that is, that's going to give us this one, plus I sine of 90 degrees plus 360 n degrees over 3. Okay, so let's simplify that. Here, the third root of 1 is still 1. So let me just write that as 1. Here, if I take the cosine of, I can divide these things by 3. 90 divided by 3, that's 30 degrees. And 360n divided by 3, that's 120n degrees. So here I'm just dividing everything by 3. And I'll do the same thing over here. Just like my nth root theorem says, I'm dividing everything in the argument by that index. All right. So there we go. There's the nth root. In this case, the cube root. But like we said before, it looks a little strange to write an answer in a way that's different from the original problem. Here, this was given in rectangular form. We turned it into polar form. So let's go ahead and rewrite our answer back in rectangular form. Well, but which one? What do you mean, which one? Well, here, you never told us what n is. So should I have n equal to 0, 1, 2, 3, 4, 5? Which one do I use? Well, I don't know. Let's try a few of them out and see what happens. So here, let's see what happens. Let's let n equal to 0. Okay, well, if n is equal to 0, that's going to be 1 times the cosine of 30 degrees plus nothing, plus I sine of 30 degrees. And again, that's plus nothing. Okay, so there we go. And we can convert this back into the rectangular form. I know the cosine of 30 degrees. That's going to be root 3 over 2. And I know the sine of 30 degrees, that's going to be a half. So it looks like that. Root 3 over 2 plus I root 2. Okay, so what? Well, let's try another one. Let's let n equal to 1. Okay, well, I mean, won't that give me the same answer? I'm just looking for the cube root of I. I should just get one of those. Well, let's see. That's 1 times the cosine of, that's 120 times 1, which is still 120, plus 30. Oh, well, that's 150. And same thing over here, plus I sine of 150. Okay, and I know what those numbers are. Cosine of 150 degrees, that's going to be negative root 3 over 2, plus I, the sine of 150 degrees, that's 1/2. No, but those aren't the same answer. They're similar, they kind of look the same, but they're definitely not the same because look, these have different signs. So here I found a second answer. I found another thing that would work as the cube root of 3. Well, let me keep going. Let's see. Let's n equal to 2. Well, that's going to be 1 times the cosine of, all right, well, if 2 times 120, that'll give me 240, plus another 30, that'll give me 270, plus I sine of 270. And I know those numbers. The cosine of 270, that's going to give me negative 1. But if I take the sine of 270, I'm going to get 0. Oh, no, actually I have those backwards. Cosine of 270, that's equal to 0. And then plus I sine of 270, that's equal to 1. Oh, notice that's different still. That's 0 plus 1i, that's I. These are different numbers. Well, it looks like I have a bunch of answers. Let's keep going. Let's say n is equal to 3. Well, that's going to be 1 times the cosine of, let's see, if I take 3 times 120, that's going to give me 360, plus 30. Well, that's 390, plus I sine of 390 degrees. The cosine of 390 degrees, that's root 3 over 2. Plus I times the sine of 390 degrees, that's 1/2. Like that. Oh, but that one's not different anymore. Look, that's the same as this one. Well, sure, it's the same as this one. If n was equal to 3, they gave you 3 times 120, that's 360. 30 plus 360, that just brings you back around full circle. Every time you add 360, you get back where you started. The reason these are different is because you're not adding 360. Here, you're starting with by adding nothing. Then you're going to add 120, which doesn't get you full circle. Then you're going to add 240, which still doesn't get you full circle. But then you're going to add 360. Oh, and that's where that goes away. That's where you no longer have a unique answer. So here, these are the same. And notice if I keep going, I keep getting more of the same. If I do 4, that's going to be cosine of 4 times 120. That's going to be 480 plus 30. That's going to be 510. And then same thing over here, I sine of 510. But if you take the cosine of 510 degrees, that's going to give you negative root 3 over 2. And if you take the sine of 510 degrees, that's going to give you a half, which you notice is the exact same thing that we have over here. So once you get past this third one, you don't get unique answers. You just sort of start repeating your answers over and over again. Wait, how many am I going to go? Oh, well, once you get past the third one, that's it. They stop having unique answers. So how many am I going to have? Well, I'm going to have 3 separate distinct answers. Well, sure, it's a cube root. You say, what do you mean, sure? That's never happened before. Whenever you take the cube root of something, you always just get one number. For example, the cube root of 8 is 2. All right, if I type my calculator, I get the cube root of 8. That's going to give me 2. Oh, my calculator shut down. All right, there we go. So we have, if I take the cube root of 8, I just get 2. That's never happened before, that I've gotten more than one answer. Every time I take the cube root, I just get a single number. Well, yeah, but that's because calculators don't know how to handle complex numbers. But we do. You say, well, okay, but you just sounded so sure that makes sense. Why would that make sense? I mean, we've never gotten multiple roots before. Sure we have. If you take the square root of a number, if I take the square root of, so here, let me start off with this. If I say x squared is equal to 9, if I'm going to take the square root of a number, there's not just one square root. When I take a square root, I get 2 answers, plus or minus. So here, I get 2 answers to the square root. I get positive 3, but I also get negative 3. And that's always happened. Anytime I take a square root, I get 2 answers. So why shouldn't it be that every time I take a cube root, I get 3 answers? Well, the reason it hasn't been before is because those answers require you to know how to take the roots of complex numbers. But now we know how to do that. So here, the question, find the cube root, is actually not correct. It's not find the cube root. It's find the cube roots. Every time I take a square root, I get 2 answers. Every time I take a cube root, I'm going to end up getting 3 answers. If I take a 4th root, I'll get 4 answers. If I take a 5th root, I'll get 5 answers. The index of the root tells me how many roots I should get. So here, my answer is I have 3 cube roots of I. They're going to be, let's see here. That's going to be root 3 over 2 plus 1/2 I. Another one's going to be negative root 3 over 2 plus 1/2 I. And the last one was, and as I'm saying this, I noticed I made a mistake here. The sine of 270 degrees is negative 1. So this one should be negative I. And here we go. These are our 3 cube roots of I. There is one thing to notice here, and that is, notice what happens if you graph these 3 numbers. Put them on the complex plane. Okay, so that's going to be root 3 over 2 plus 1/2. Okay, so let's see. Root 3 over 2, that's root 3 divided by 2. That's about 0.87. Okay, so I'm going to go forward almost all the way to 1, and then up half. So that's going to go right there. Okay, negative root 3 over 2 plus 1/2. Well, that's going to go the same amount, but instead of going to the right, that one's going to go to the left since there's a negative. And then again, I'm going to go up I'm going to go up 1/2. So right about there. And then the third one is, negative I, which is down this way. Notice how those are evenly spaced? That is not a coincidence. Whenever you take the roots of a complex number, all the roots are going to have the same modulus, right? Because of course all the modulus come from the same number. They come from the root of the original modulus. These arguments are going to be evenly spaced out. So if you have something, if you're looking for the cube root of a number, you're going to have 3 evenly spaced numbers. Here, this angle will be the same as this angle, which is the same as this angle. If you had fifth roots, you would have 5 of these, all evenly spaced out, where the angles in between are all going to be the same. Right? That's a nice visual confirmation that what we've done is correct.